Well, welcome back. And here we are again. Today, we're going to be talking about momentum. What is momentum? What is some important things about momentum that we want to keep in mind? All that good stuff. So, let's start. What is momentum? Well, its definition would be something along the lines of it is an object's quantity of motion. Or maybe it's put as the momentum of an object is the product of its mass and its velocity. So in other words, it just looks like this. P is your momentum, lowercase p, equals mass times velocity. Okay, the units for that, well, mass is measured in kilograms, velocity measured in meters per second, so we can write kilogram meters per second as our unit for momentum. Great. Now, momentum becomes exceptionally important in the realm of physics because it is conserved. It's one of those things like conservation of charge, conservation of energy, where if you are trying to come up with some new theory, if you find that momentum in a closed system is not conserved, you're wrong. Now, let's talk about this idea of conservation of momentum. Okay, so what does that mean? Well, in a closed system, which means you have a set defined set of things, the total momentum before something happens will equal the total momentum after something happens, right? Sometimes I'll call that like an event. Now that event could be either a collision or some sort of separation, which we're going to get to in a second. All right, so conservation of momentum basically can be kind of boiled down to this. Okay, so conservation of momentum, the momentum before equals the momentum after. Okay, so before and after what? Well, as previously stated, we're going to talk about different events that can occur. Okay, so there are three main types of collisions that we're going to deal with, and then another kind of, I call it a separation. Sometimes you might hear it described as an explosion or this or that, whatever. It's the same basic idea. Okay, so let's start with some collisions. The first kind of collision is elastic. Elastic collision. Okay, so basically what happens in an elastic collision is you have two objects, they collide, then they bounce off each other. So here's my two objects, they're going to collide, they're going to bounce off each other, and this is the important part, kinetic energy is conserved. Space. Okay, so kinetic energy is conserved in an elastic collision. Okay, now, of course, in any closed system, we know that energy as a whole is conserved. What makes elastic collision so special is that specifically specifically kinetic energy is conserved. Okay. Now, in real life, we only ever really deal with or observe inelastic collisions, which is the next kind, right? The reason being we don't see too many elastic collisions is because energy is often lost to heat due to friction between the two objects or sound, right? You can hear a collision, that kind of stuff. So the kinetic energy is not conserved there. Alrighty, inelastic, same idea. The two objects collide, but they bounce off each other, but Ke, kinetic energy, is not conserved. Okay, so in an inelastic collision, the kinetic energy is not conserved. Right? The math, the basic look of a conservation of momentum problem for elastic or inelastic collisions look the same. Right? You have two objects before the collision, you have two objects after the collision. But what's different is when you go in a little bit deeper and calculate the kinetic energy of the system before and after. Right, you'll find that the kinetic energy after is not conserved in an elastic collision. Okay, now the next type would be perfectly inelastic. All right, ran out of space. So what that means is the two objects collide, but they stick together. Right, sometimes this could be just two blocks that end up colliding and moving together, or two carts that somehow latch together. Sometimes it's an arrow going into a block of wood, or a lump of clay hitting a block, right? Anything that the two objects are going to and stick together with, okay? Since it is an inelastic collision, kinetic energy is also not conserved. All right, so those are your three basic collisions, okay? The last type of event we're going to talk about before we move on just a scotch is a separation, okay? Now, again, sometimes these are called explosions, but it doesn't have to be such a big type of scenario, right? Basically what you have is you have two objects that are in contact, or maybe it's one object that's going to break, whatever, okay? At some point, they're going to separate. And due to the conservation of momentum, they're going to end up going in opposite directions. Okay? Although it's also possible if this thing as a whole is moving this way, maybe there's enough for it to kind of this one to slowly go that way too. Right? You figure it out within your problem. Okay? In a separation, kinetic energy is not conserved. Again. Okay, so it's really just the elastic collisions that have that conserved kinetic energy. All right. Now, we are going to do another video, or I'm going to do another video since I'm the only one here, where I'm going to go through a practice problem for each of these scenarios, okay? So keep an eye out for that. One more thing I do want to talk about when dealing with conservation of momentum problems is something having to do with the center of mass, okay? The center of mass. An object's, or a system's center of mass, the way it's moving, the velocity of that center of mass is conserved. So here's an example. Let's say I've got an object that's split into two pieces, or it's two pieces to begin with, right? A square piece and a triangle piece. And let's say, for example, this is moving to the right with a speed v. Right? Now, at some time later, t, whatever, who knows if they give you an actual number, right? These two things are going to split apart, right? Could be like a two-stage rocket type of thing, whatever, right? They're going to split apart, okay? You might see that the square moves off with some speed and the triangle moves off in the other direction with some speed. But what's important is the center of mass, the velocity of the center of mass, v sub com for center of mass, stays moving to the right at speed c. Okay, this is true for any of these collisions. This is true for any separation, whether they stick together, not stick together, they split apart, whatever. The center of mass's velocity will remain the same before and after the event. Right? It all has to do with this idea of conservation of momentum. All right, so like I said, I'm going to do another video on some practice problems for conservation of momentum. We'll do one for elastic/inelastic collisions, one for perfectly inelastic collisions, one for a separation, and that should do it for that. All right, so with that, I'll see you next time.